If we are given that means you derive the equation of the motions. Okay, so let me put into this. And here, for example, here is subject to the general force and with the initial conditions. So basically, those one are the M is a square matrix, and this is the column matrix. Okay, so basically here I draw the size of the information here. So basically, those are the elements, arrangement of elements, something like this one. Okay, so you know that is an n-dimensional. So the same thing. This is the element. So depends on the degree of freedom. Okay. So right now, I think to this moment, you must know how to determine the natural frequencies. Okay, determining the natural frequencies simply is we take the determinant. Let me skip up the details. Basically, that is minus omega squared times m plus k. And we proceed the calculation like this. Then for each natural frequencies, you solve for omega I. Okay, I is 1, 2, 3, 4, etc. Then for each natural frequencies we solved, then you're going to calculate the associated, we call the eigenvectors, and here in terms of vibration, we call it vibration mode. Okay, and in our notations, we're using such a notation, capital X. And again, the contents of the capital X, again, that is certain element in column vectors. Okay, so that's the contents. Then that is the starting point of we call the modal analysis. And that is, I put into homework 13 for you to exercise, okay? The modal analysis, which is based upon the orthogonalities. Of the modal vectors, okay? So, given for modal vectors or vibration mode, okay, so let me say this one. And we can normalize these modal vectors in such a way, any modal vectors, and take transpose, multiply with M matrix, multiply with this modal matrix, and equal to 1. Okay, and in terms of the dimensions, basically that is like this. The transpose, this is called the transpose. So that is, we have such an element, and that is row vectors, and multiply with square matrix, and multiply with column vectors. So basically, the calculation result should split into 1 to 1, 1 by 1 scalar factors. So something like this one, okay? So doing the normalizations, and so in this way, we from this point we start with normalized model vectors or vibration mode. Then we have such a properties for each model vectors transpose multiply with n and multiply with this one equal to 1, and then let me put into this way. We define the model matrix. Okay, start with the normalized. Okay, so model matrix we define as a capital X, and that is a collections of the model vectors in each column. So that is X1. So that is a column vector, and I use this one to indicate that's a column vectors. Okay, and second model vector, and that's a column vector, and you simply collect all the model vectors into this matrix. Okay, so from here we know transpose times n times this equal to identical matrix 0, 0, and then we have transpose K matrix, and with this one equal to omega 1 square and omega n square, and that is 0, 0. Okay, so everything starts from here. So with this one in mind, then we can begin to do something. So the equation of the motions, let me repeat, we copy that here. So that is given by m x double dot plus k x equal to f. Okay, this is not correct. And if we start from here, we know that for all the solutions can be in linear combinations of the model vectors. Okay, so that is the most essential part of the multiple degree freedom vibration solutions. So this one, we know that can be decomposed into the combination of the model vectors and will be written into a precise form. That one simply is this. This is the model matrix. Multiply with Q. Okay, so this one, if you expand it, this is a very concise expression in matrix form. But if you try to expand it, basically you expand it in this way. X1 plus Q2T, X2 plus QNT, Xn. Okay, so basically once you expand it, that is, for each, that is the model vectors. And X, Q1, Q2, Qn, that's called the combination coefficients, and which is time dependent. Okay, so keep these things, we plug into here. So equation of motions become like this: M capital X Q double dot plus K capital X and Q equal to half. Okay, so I leave a little bit of space here because I want to utilize the two properties here. Okay, to utilize that one, simply I pre-multiply this equation with transpose of the model matrix. Okay, so I pre-multiply in such a way that you can see basically this one becomes identity matrix 1, 1, 1, 0, 0. And then this one becomes omega 1 square, omega 2 square, omega n square. Okay, so this one, basically here, this one is a matrix multiplied with a column vector. So that one is a new column vector. Let me define it as a Q1T, Q2T, etc. QNT. So therefore, in such case, you see this one is we call the decoupled system. We have Q1 double dot plus omega 1 squared Q1 equal to Q1T, and etc. Qn double dot. Okay, so that means here the original equation of motion basically can be decoupled into a combination of simple combination of a simple single degree vibration systems in terms of Q, right? And this one basically multiplied by doing this. So what is the initial conditions? So we need to take care of the initial conditions. The initial conditions is simply doing by this, and we have to do it separately. So let me write it up here. Let me start from here. Okay. Okay, let me copy that one here. So we know the expressions x of t is equal to have these expressions. Okay. So again, starting from this is again the copy from there. I pre-multiply the equations with capital T transpose with n, and this one is n. Transpose. Okay. So let me rewrite this one and have a way to see. Okay. So based upon this again, this is an essential part. We're saying the general solutions is the combination of the modal vectors. Okay, so I copy that information from here and I pre-multiply with such two terms. And again, I want to utilize the very good properties here. In particular, I use this one. So I pre-multiply and such that this equation can appear. So that is this one appear here. This one equal to 1, 1, 1. So this is the identity matrix. If you remember the handout I gave to you, any vectors or anything multiplied with one identity matrix equal to itself. So this one basically, this one equal to Q. So therefore, from here we have the very general expressions simply equal to this. So given any x, we can have a corresponding Q. So therefore, the Q initial conditions simply equal to this. And the similar way, the initial velocities have the same patterns. And again, for this one, this is column vectors of so many components. Okay, so this is again, this is a column vectors with certain components. similar way. So basically, once you conduct these calculations, then you should have this number here, you should have a number here. Okay, so now we can proceed using the examples last time we have, and let me demonstrate. Okay, so keep everything, that is everything we need. That is everything you need for final exam. In addition to any lecture notes for help yourself solving such kind of equations, this is the undamped equation, vibration, single degree freedoms. If Q is the harmonic, then you go to chapter 3, right? If Q equal to 0, then you go to chapter 2. If Q is any non-periodic or any general function type, then you go to chapter 4. Good? Okay, so I can tell you this board summarize everything you need for, in particular for final exam. Okay, so let's continue the example we have. So last time we come up